Welcome to Lecture 1B. We are continuing with Systems of Linear Equations. There is a reading homework associated with this lecture that is due on Thursday. We are interested in solving a linear system. And by solve, I mean to find solutions of a linear system. Our general strategy would be to use operations called elementary operations to transform the system we are interested in into another system that is equivalent. And the equivalent system means so we say that two systems are equivalent if they have the same set of solutions. But the reason why we would want to go to a different equivalent system is because it's possible to get to an equivalent system that is easier to compute. So that is what we will do. The three elementary operations are here. So we can exchange two equations. And if we do that, we do not change the solution to the system. We can also multiply one equation by a non-zero number. We can add a multiple of one equation to another one. Doing any of these three operations will not change the solutions of our system. And in fact, so the three elementary operations have different roles in this course, but for what we're doing right now, the last operation here is the most useful. Now I will do a computation where I use elementary operations, and I'll only use the second and third. I will use them to find a solution to this system of linear equations. And I encourage you to follow along and do the computation on your own paper, and pause the video when necessary. I have just copied the original system, and now I'm going to apply the operation of multiplying the second equation by -1. So I multiply both sides by -1, and that gives me this equation. So this is a system of linear equations which is equivalent to my original. And now, because my goal is to find a solution, I want to try to simplify the system. I noticed that if I add the first and second equations, I would cancel out x and y. So I will do that. I will apply this third operation where I replace my second equation with the 1 times the first equation and the second equation. So I have x minus x, which is equal to 0, and y minus y, which is equal to 0. Z minus 2z is equal to -z. 3 minus 4 is equal to -1. And this is my new system of linear equations. And here I notice that it is enough just to look at the second equation to be able to say what the value of z should be. So z would have to be equal to 1. And now I want to find the other values. And now I will do what's often called back substitution. I substitute z equal 1 into one of the other equations. And I will substitute it into the third equation because I see that it is simpler than the first equation, because the third equation only has 2 variables. So I substitute 1 here. So the value that I have is y plus 2 times 1 equal to 2. So that means that y would have to be 0. And now I have the values for both z and y. I will substitute those into the first equation. So I have x plus 0 plus 1 equal to 3. And this tells me that x would have to be 2. So we've shown that this triple of numbers, 2, 0, and 1, is in fact the unique solution to the linear system. There is only one solution. So now let's do a sanity check. Let's check that this solution, this triple, is in fact a solution to the system. So to do that, I should substitute these values into each of the 3 equations. And you should confirm this on your own. So for the first one, I have 2 plus 0 plus 1 equal 3. So that checks out. So you should do the same thing for the second and third equation. What I just did earlier is a strategy where I eliminate variables by adding multiples of one equation to another, and also multiplying an equation by a non-zero number. And then in what just happened, I did find the value of one variable. And once I found that value of z, I just substituted into the other equations. So I did the back substitution. And this works pretty well for like small systems and scratch paperwork. But it's not maybe the most efficient method in general. So in the next video, we will improve this, and we will talk about an algorithm. And another issue with this strategy, the thing that I just did, is that it's not very clear how my strategy would deal with when the system has multiple solutions, more than one solution, or no solutions. Now I want to introduce a time-saving notation. So remember that for a system of linear equations, the variables for all of the equations are the same, right? Like here we have x, y, z, and we have that for all of the equations. So we don't really need to write down the variables. What we really need to keep track of is the coefficients and the constants. Remember that the coefficients are these numbers in front of the variables. And the constant terms are the ones here. And when we're doing elementary operation, we really need to only keep track of the coefficients and the constants. And we can do this with what's called an augmented matrix. So what it is, it's really just you put numbers in a grid and you put brackets around it, and then you put this vertical line between the coefficients and the constants. So really it's just like taking this system of linear equations, but I remove the variables. And then instead of the equal sign, I put this bracket. And then sometimes for clarity, people might write like commas when the coefficients are big. In slide number 3, we talk about elementary operations on linear systems. Now that we use a shorthand, instead of writing the equations, we write a linear system as an augmented matrix. Our elementary operations then become elementary row operations. So instead of exchanging two equations, we exchange two rows. Instead of multiplying one equation, we just multiply one row by a non-zero number. Right, so this, I don't think I mentioned this, but this is an important piece, because if you multiply an equation by zero, in general, you might not get another equation that is equivalent. And instead of adding a multiple of one equation to another equation, we add a multiple of one row to another row. So here, this should also be, well, no. So this could be, so I was going to say that I should have put a non-zero number, but adding a zero multiple of one row to another row would just be not doing anything. So that is okay also. So now I will do another example where I start with this system and I convert it into an augmented matrix, which we did in this slide. And then I will use that augmented matrix and apply elementary row operations to simplify it. And then I will determine the solutions of the system using the augmented matrix shorthand. And I encourage you to follow along on your own paper and pause the video as necessary when you're doing your computation. So we've done this first step. And now I want to use elementary row operation to simplify the augmented matrix. And to simplify an augmented matrix, we want to have as many zero entries as possible. So right now, none of these have zero entries, but I know that I can turn this entry into zero if I replace this whole second row with -5 of the first row plus itself. So I can do -5 plus 5, that's 0. And then I can do -5 times 2, which is 10, or -10. And -10 plus 6 is equal to -4. And I keep going in that fashion, and I get this new second row. And now the next thing that I'm going to do is I'm going to replace this third row in such a way that this 9 is going to turn into a 0. And the way that I will do that is I will replace this third row with -9 of the first row plus the third row. So that's a typo. Okay, and now I encourage you to pause and check that what you would get when you do this operation is this new third row. From here, there are several different elementary row operations that would make sense, that would simplify the augmented matrix. But in this note, I have chosen to do the following. So I will multiply the second row with -1/4, because that would make these integers smaller. So multiplying this second row by -1/4 gives me this row. And I see that I could also simplify the third row by multiplying with -1/8. And that gives me this row. Now I see that these second and third row are equal. And whenever we see that, we can just disregard one of them. It doesn't give any new information. But right now we are practicing elementary row operation. So now I will use the elementary row operation, which is to replace the third row with -1 of the second row plus itself. And that gives me this new third row of all zeros. So from here, we can continue applying elementary row operations to simplify the augmented matrix even further. But right now I'm choosing to stop. And now I'm going to convert this augmented matrix into a system of linear equations. So all I do is put back the variables in front of the coefficients and then replace the vertical line with equal signs. So I get this linear system. And even though I've written down 3 equations, the last one is really just 0 is equal to 0. So that is not really useful information. So our system can be described with just 2 equations. And because what we have done so far, we've only done elementary row operations. So this new system is equivalent to the original system. And remember that equivalent means that they have the same solutions. And as you can see, this blue system is simpler than the brown system. So I will use this simpler system to do back substitution. So here I see that the second equation is simpler than the first equation. So I do that first. So from here, I can conclude that y is equal to 3 minus 2z, right? I would just move the 2z to the right. And now I can substitute this y into the first equation. So this is the first equation. And what I'm doing here is just I move 2y and 3z to the right. And then I just substitute y with 3 minus 2z. And as I'm simplifying, at the end I get x is equal to -2 plus z. Now I can conclude that the set of solutions of this system, this original system, is the set of triples that can be written in this form for any t. So here, t is called a parameter. So because you can use any t, and by the way, I have replaced the z here with t, and yeah, and here is x, and here is z. I've replaced z with t to make it clear that it's a parameter. So this solution has more than one, or this set of solutions has more than one triple. Because, for example, I can just, if t is equal to 0, I can put that in here and I'll get a triple. I can also do like t is equal to 1/2 and I'll get a different triple. In fact, there are infinitely many solutions. In contrast to the last exercise we did, exercise 2. What we've done so far is talk about a general problem for finding solutions to a system of linear equations. We also talk about the tools for simplifying that problem called elementary operations. And so far we've done this vague strategy where we try to eliminate variables and do back substitution. And we use this time-saving notation, the augmented matrices, which we will continue to use because it's convenient for computation. And some questions that you can think about for the next lecture is when is a system of linear equations easy to solve? And we will answer that next time. And I sort of mentioned how I decided which elementary row operation to use, but I'll talk about that more. And we'll also talk about how can we tell if we have no solutions or multiple solutions, and how can we do it more quickly. So matrices will show up like very often in this class, and we'll look at many different structure in matrices. But for right now, you can think of augmented matrices as just a notation to store numbers in a grid, like an Excel sheet. This is the end of lecture 1B. Remember to do the reading homework by Thursday.